Hello friends, welcome to Abdemi. Today we will consider an interesting problem on magnetic fields. See, what's the statement of the problem? See, it is a long horizontal wire AB is a long horizontal wire which is free to move in a vertical plane and carries a steady current of 20 ampere, is in equilibrium at a height of 0.01 meter over another parallel long wire CD, which is fixed in a horizontal plane and carries a steady current of 30 ampere, as shown in this figure. Show that when AB is slightly depressed, it executes simple harmonic motion. Find the period of oscillation. So this is the diagram of this problem. CD is a long wire which is held horizontally which is fixed in a horizontal plane and carries a steady current of 30 ampere, and AB is another wire, long wire, which is free to move in a vertical plane. So it can move freely in the vertical plane and carries a steady current of 20 ampere. One point you note, what is the direction of current that has not been mentioned in this problem, whether both are carrying current in the same direction or they are in the opposite direction, that is not being mentioned over here. So before we proceed to solve this problem, let us do some recapitulation. See this diagram. What is that? When two conductors carry steady current, two conductors, this is one wire, long wire, wire 2 is another long wire, they are parallel to each other, and wire 1 is carrying a current I1 and wire 2 is carrying a current I2, and they are separated by distance d. Now, due to the current flow through the wire 1, there will be a magnetic field in the space surrounding the wire 1 where wire 2 is kept, and since wire 2 is carrying a current, when a current carrying conductor is placed in a magnetic field, then it experiences a force. And similarly, that means due to the presence of current carrying conductor wire 1, wire 2 will experience a force. And similarly, wire 2, since it is carrying current I2, it will produce a magnetic field surrounding wire 2, and since wire 1 is in the surrounding space of wire 2, and since it is also carrying current, therefore wire 1 will also experience a force. That we have learned in our studies on magnetic fields produced by electric currents. Now, what is if F1 is the magnitude of force on L1, L1 is this one and this is L2. L1 is the length of the wire 1, L2 is the length of the wire 2. Magnitude of force on L1, length of wire, L1 is this is wire 1, and consider a length segment L1 of the wire, and similarly wire 2 is also very long, and consider a length L2 of the wire 2. Now, magnitude of force on L1, if I call it F1 is the magnitude of force on L1, length of wire 1 due to wire 2, and similarly F2 is the magnitude of force on L2, length of wire 2 due to wire 1. Now, this formula we have learnt already, that F1 divided by L1. That means what is the force experienced on unit length of wire 1 due to presence of wire 2? It is actually mu naught I1 I2 by 2 pi d, and it is a vector quantity y cap. Y direction is this direction, this is y direction as per this diagram. This is z direction, and the perpendicular on this board, this direction is x direction. So force per unit length on wire 1 will be mu naught I1 I2 by 2 pi d y cap. That means it is directed, this force is directed in the positive y direction. Similarly, F2 by L2, which is nothing but the force per unit length experienced by wire 2 is negative mu naught I1 I2 by 2 pi d y cap. And y cap is this direction, y is along y direction, y cap, and therefore F2 by L2, this vector has a direction in this direction. Alright, and you see we have drawn I1, I2 in the same direction. Both the conductors, both the wires carry current in the same direction, they are parallel to each other. Now this we know from our basic courses. This formula will be useful in our calculation. One thing is that force per unit length are equal in magnitude and opposite in direction. The forces are attractive. See why these forces are opposite in direction? Because F1, that means F1 by L1 is the force on wire 1 due to presence of wire 2, it is in this direction. Whereas F2 by L2, this vector, which is the force experienced by wire 2 due to presence of wire 1, it is in opposite direction. And both the forces are equal in magnitude because it is magnitude is mu naught I1 I2 by 2 pi d. Mu naught is the free space permeability. Mu naught, you know, it is free space permeability. Alright. Now that means when the currents are in the same direction, then forces are attractive. Like this, what we have shown. It is in this direction as if wire 2 is attracting wire 1 and wire 1 is attracting wire 2 because this force is in this direction. But if I1, I2 are in opposite direction, that means if one current I1 is in this direction, I2 is in opposite direction, then F1 by L1, since I1, I2 are in opposite direction, so F1 by L1 in this case will be negative mu naught I1, I2 divided by 2 pi d y cap, because I1, I2 product will be negative in this case. Here they are in the same direction, so product I1, I2 is positive. If I1, I2 are in opposite direction, then the product I1, I2 will be negative, and F1 by L1 will be negative mu naught I1, I2 by 2 pi d y cap, whereas F2 by L2 will be mu naught I1, I2 by 2 pi d y cap. That means that will be in the positive y direction, whereas this quantity will be in the negative y direction. So it will be repulsive. So it will experience force. F1 by L1, it will experience force in this direction, whereas it will experience force in this direction. So the forces are repulsive if currents are in the opposite direction, and the forces are attractive if the currents are in same direction. With this background, let us try to solve the problem. I hope this is clear. So when both conductors carry current in the same direction, there is each forces on the wires. It is carrying current I1, it is carrying current I2, and the forces will be attractive in nature. It will experience a force in this direction, it will experience a force in this direction. Whereas if the wires carry current in opposite direction, like this, whatever you have shown, then it will experience a force in this direction, it will experience a force in this direction. It will be repulsive in nature. Alright, y direction is this direction. This is positive y direction. Now with this background, let us try to solve this problem. Now, what happens? Let us see. What is the direction of current flow in this conductor? That let us try to find out first. It is not mentioned. See, both the wires are actually in the vertical plane. Okay. Now this CD wire is fixed, so it is kept fixed by some mechanism. But AB is actually in equilibrium because of what? Because on AB there is a weight. It is experiencing a gravitational force which is nothing but mg, where m is actually mass per unit length of wire AB. Mass per unit length of AB. So, just let us consider per unit length basis what are the forces acting on AB, wire AB. So, there is a gravitational force downward in direction, downward direction. Therefore, the magnetic force experienced by AB must be in the opposite direction to keep the wire AB in equilibrium. It cannot be in the downward direction. Since AB is in equilibrium at a height of 0.01 meter, when the distance is 0.01 meter, then the wire AB is kept in equilibrium position, and therefore the magnetic force experienced by wire AB because of presence of current carrying conductor CD must be in the opposite direction. Therefore, the currents in both the conductors must be in the opposite direction. If it is in this direction, CD is in that direction. It must be in the opposite direction. So, they are in opposite direction. And what has been told? That here the AB, where AB is carrying a current 20 ampere, we call it I1, whereas it is carrying a current 30 ampere, I2. And definitely they are carrying current in opposite direction, so that there is a repulsive force between them. Because of presence of wire CD, AB experiences force in the upward direction and it is getting balanced by the weight. Alright, now consider a coordinate system. This is actually considered x direction, and this you call the equilibrium position, you call it 0 position, and this is x direction, you can call it capital X direction. Alright, this is the 0th position, equilibrium position. This is equilibrium position, you can say. Position of wire AB. Therefore, since it is in equilibrium position, so m I have considered m is the mass per unit length. So, weight per unit length, downward gravitational pull per unit length, downward gravitational force per unit length on AB is definitely mg, and d is, call this distance as d, which is nothing but d is equal to 0.01 meter. And what is the force experienced by AB due to presence of current carrying conductor CD per unit length? Magnetic force which has to be upward to keep the wire in equilibrium position, magnetic force upward per unit length of AB is actually Fm. That means magnetic force per unit length of AB I can write is equal to mu naught I1 I2 by 2 pi d. There is no doubt about it, we can write like this, and therefore I can write mg in the equilibrium position, mg equal to mu naught I1 I2 by 2 pi d. Up to this, I think there is no confusion. So in equilibrium, mg equal to mu naught I1 I2 by 2 pi d. All right. So let me write down mg mu naught I1 I2 by 2 pi d equal to mg. This is very important result. Let me remove whatever you have written over here. I think you have noted down. Now what is happening? The where AB is depressed slightly, that means it is pushed downwards in the downwards direction by a small, very small amount. So what happens in that case? As soon as it is depressed slightly, see, the position of CD is kept fixed by some mechanism. It is understood that position of CD is kept fixed. Now when AB is slightly moved or pushed in the downward direction by an amount small x, then what happens? The separation between where AB and CD decreases. Now if it is depressed to the position A dash B dash such that the separation is x, that means the coordinate of A dash B dash is x, you can say it is little depressed, then the separation between AB and CD becomes d minus x. And in this situation, when the wire is in A dash B dash position, then what is the downward pull? Downward force per unit length on the where AB when it is at A dash B dash is how much? It's same, it is mg. Downward force, which is the weight per unit length, which is nothing but weight per unit length of AB. No doubt, because I already told that M is the mass per unit length of the wire AB. So downward force per unit length on the wire AB when it is at A dash B dash position is mg, which is in downward direction, weight per unit length of AB. Now, what is the upward force? Upward force per unit length on AB when it is at A dash B dash position is how much? Equal to, we call it mu naught I1 I2 by 2 pi d minus x, and this is in the upward direction. All right, so what is the net downward force per unit length? On AB. On AB, always we are talking about AB, which is at the position A dash B dash now, is actually mg minus mu naught I1 I2 by 2 pi d. This is the net, and d minus x. Okay, so it is, once again I am writing clearly, it is mu naught I1 I2 by 2 pi d minus x, because separation is now d minus x, and therefore the magnetic force which is repulsive on AB per unit length is actually mu naught I1 I2 by 2 pi d minus x. But mg is already we have calculated, these two are not equal, it is not 0, because mg is only equal to mu naught I1 I2 by 2 pi d. So this is non-zero force. And what is this value if I want to calculate? We know mg is actually this thing in the equilibrium position. Mg is mu naught I1 I2 by 2 pi d. So I write, in place of mg I write net downward force per unit length is actually mu naught I1 I2 by 2 pi it is, once again, it is mu naught I1 I2 by 2 pi 1 by d minus 1 by d minus x. So it is actually what? Mu naught I1 I2 by 2 pi d into d minus x, and here d minus x minus d, so it is negative of x in the numerator, but x is much less than d, so d into d minus x I can write as d square, because x is very, very small compared to d. Therefore, the net downward force per unit length, it becomes how much? It becomes minus mu naught I1 I2 x by 2 pi d square. So net downward force, if there is a negative sound, that means actually the force is in the upward direction. Net downward force per unit length is minus mu naught I1 I2 x by 2 pi d square. And this is actually, let me write it once again so that you can note down. It is minus mu naught I1 I2 x by 2 pi d square. Alright, actually the force is trying to bring the wire A dash B dash from A dash B dash position to equilibrium position AB. And since there is a net downward force which is negative, that means it is actually upward force because x axis is in this direction. Therefore, there will be acceleration produced, and acceleration, how can I calculate the acceleration produced? I should divide, this is net downward force per unit length. Therefore, acceleration, whatever acceleration, just let me remove this part now. So, acceleration is actually mass into acceleration is force. So, acceleration produced will be how much? You have to divide this quantity by m. And acceleration I can write here, since it is in x direction, so acceleration will be d2x dt square. d2x dt square multiplied by m should be equal to this much, because this is a net downward force. Net downward force is negative of mu naught I1 I2 x by 2 pi d square. Therefore, if I call this acceleration d2x dt square, you can call it A also. So, mass into acceleration is net downward force, which is negative. Negative sign indicates that the force is actually in the negative x direction, which is negative x direction, and it is trying to bring the wire back in the equilibrium position from the position A dash B dash. From equilibrium position, you have depressed the wire slightly. So, d2x dt square is equal to minus mu naught I1 I2 by 2 pi d square x divided by m. But what is m? M is actually, from here you can write, m is mu naught I1 I2 by 2 pi d into g. So it is, I can write minus mu naught I1 I2 by 2 pi d square, then m, if I take it out up 2 pi d into g divided by mu naught I1 I2. So, and obviously there is a x. So, in place of m I have used this expression. So, mu naught I1 I2 by 2 pi d square x divided by mu naught I1 I2 by 2 pi dg. So, or I can write d2x dt square is equal to, why d2x dt square? Because this is the x direction, x is the displacement when it is in A dash B dash position, and at this position the acceleration is d2x dt square, which is actually, it get these two terms, they are cancelling each other, and 2 pi, and we are left with actually minus g by dx. So, I can call it minus omega square x. Omega square is g by d. So, d2x dt square equal to minus omega square x is the differential equation of motion of the wire, and which is the equation of a simple harmonic motion. Differential equation of a simple harmonic motion. So as soon as I find the equation of motion, one-dimensional motion, because it is free to move in this vertical plane, so its equation, if I can express like this, d2x dt square equal to minus omega square x, we can readily say it is executing a simple harmonic motion. And what is the period of this? Period is actually t equal to 2 pi by omega. What is omega? Omega is actually, omega square is how much? G by d. So omega is 2 pi by, omega is root over g by d, so it is root over d by g. Alright, so t, the period. So if I just remove some part of the calculation, what is that? So t equal to 2 pi root over d by g. You take g as 10 meter per second square. We can write like this, approximately g is 10 meter per second square. So t's value becoming 2 pi root over d. D is actually 0.01 divided by 10. So it is 0.2 multiplied by pi by root over 10, 1 by 10, pi by root over 10. Alright, and this is in seconds, obviously, it's time, it is second. And pi by root over 10 is, root over 10 is approximately equal to pi, because root over 10 is about 3.16 and pi is 3.14159. So ultimately I am left with this figure, which is 0.2 seconds. So this is the t, the period of oscillation of the simple harmonic motion is 0.2 second. So this is the answer. In the period of oscillation, it is 0.2 seconds. So see, we got the differential equation of motion like this. So from that we can say readily that it is executing a simple harmonic motion. That means when it is pushed back, there is a net upward force. That means the system tries to bring it back to the equilibrium position, and it executes a simple harmonic motion like this. Alright, and the period of oscillation is 0.2 seconds. See, ultimately in this problem, how much current it is carrying, this 20 ampere or 30 ampere, they are not coming into picture, they are not necessary. Value of mu 0 is also not required. Ultimately, the expression for period is this much and value is 0.2 seconds. So this is a problem where actually from basic conception you have to proceed. You have to find how the wire AB can be kept in equilibrium position. And we understood that definitely the currents in both the wires should flow in opposite direction. Had it been in the same direction, the wire AB will not be in equilibrium position. Initially it is at equilibrium. Now if it is slightly depressed, then it will start executing simple harmonic motion, and differential equation of motion will be like this, and period of oscillation will be 0.2 seconds. So this is a beautiful problem. Many concepts are involved in this. So I hope you have understood the concept behind the problem and the technique how the problem could be solved. So if you understand the basic concepts very well, you can solve problems which are not very complicated. Simple ideas are only essential in solving these problems. I hope it was useful to you. Thank you very much. Thank you for listening to this video. Thank you.